So today we're continuing our lessons on circles, albeit relatively brief. I've actually kind of cut this one down just a little bit as well. Last Thursday, we talked about central angles and how if you took that angle measurement, it equaled the arc that it intercepted. Those measurements were exactly the same. That allowed us to kind of work our way through a circle, find different angles, find different arcs. We also had a formula for calculating the length of an arc. That basically took the degree measure of that arc times the circumference divided by 360. So we had a formula for that as well. Today, we're looking at a few more relationships dealing with angles and arcs. But instead of central angles today, we're looking at inscribed angles. So just as a quick recall, I know we took lots of these notes last week, but an inscribed angle is an angle with its vertex on the circle with two sides that are chords. Now, we're going to be using a term today known as an intercepted arc quite frequently, which is just the arc that lies between the endpoints of an inscribed angle. Now, there is a very specific relationship similar to what we used last week with central angles. So central angles equaled the measure of their intercepted arc. Today, the degree of of the inscribed angle is equal to half the measure of its intercepted arc. So taking a look at this diagram here to the left, here we have inscribed angle ABC in circle P. It is intersecting, let me see if I bring out my tool here. It has an intercepted arc of AC. And the measure relationship between the two is that the measure of angle ABC is equal to half the measure of arc AC. Or if you wanted to think of that in reverse, AC, arc AC is twice the measure of angle ABC. So depending on which way you're going, one is half the other, one's double the other. Both ways there. Now, from that relationship and based off of how inscribed angles can find themselves inside of a circle, there's two special scenarios to consider. See if I can squeeze these on here. The first one is when it's intercepting a diameter. So you have an inscribed angle, it's intercepting a diameter, which is a chord that goes through the center. It creates two semicircles. What happens is that if an inscribed angle intercepts a diameter, then it is considered a right angle, just automatically. So in the example provided here, the measure of angle BAC is going to be 90 degrees, which hopefully doesn't shock us too much because a diameter, like I said, forms two semicircles. Semicircles have what measure? How many degrees is a semicircle? 180. 180. If an inscribed angle is half the intercepted arc, and this intercepted arc is a semicircle, half of 180 is 90. So it's a very special relationship to where even if you forgot it, so long as you could recognize that it is a semicircle and it's 180 degrees, taking half of it, you're going to get 90 each time. But it is so special that it's been specifically identified here for us. The second one here, this is actually a pretty unique relationship, is when you have two inscribed angles that intercept the same arc in the circle. So when this happens, those two angles are congruent. So if I take a look at this diagram here, we have angle ABD and angle ACD intercepting the same arc AD. Well, think about this. If those inscribed angles are half the measure of that arc, but they're intercepting the same exact arc, whatever half of that is, they are both going to be the same. So these two angles in here are going to be congruent because their endpoints are through the same intercepted arc. So the statement we would say here is that the measure of angle ABD is equal to the measure of angle ACD. So a lot of information there. The biggest takeaway, inscribed angles, the vertex is on the circle itself. That inscribed angle is half the measure of the arc that it intercepts. So it gives us some things to calculate. So we're going to try some out here. We're going to find each angle and arc measure depending on which we're provided. So here we're looking for the measure of angle WXY. What I do know is that it's intercepting arc WY, which has a measure of 62 degrees. What would be the measure of the angle, inscribed angle? Careful. The inscribed angle is half the measure of the arc. So it would be 31 here. I think you went the opposite direction.
Yeah.
So the angle is smaller than the arc, half as much. Number two, this one, again, is a little bit in reverse. This time we have an inscribed angle DEF. And because of how big it is, the arc that it's intercepting is a major arc. Oh gosh, that was painful.
So 113 is that the angle degree.
So 113 is the measure in degrees of that inscribed angle. That inscribed angle is half the measure of that arc it's intercepting, which means the arc must be 226. Quick throwback. Again, the reason why there's 3 points used to name that arc is because it's a major arc. It's greater than 180 degrees.
Let's get 226.
Doubling 113. So if you look at these two side by side, if you're looking for the inscribed angle, it's half the arc measure.
Okay.
If you're looking for the arc measure, it's double the inscribed angle. So half one way, double the other. Next one's kind of sly. What's the measure of angle PQR?
90,
How do we know that?
because it's a 90 degree, it's a right angle.
It is a right angle. I'm going to push you a little bit further. You are correct, but it is an inscribed angle. How do I know that it's exactly 90?
It intercepts the diameter.
It is intercepting a diameter. PR is a diameter of that circle, which means it makes a semicircle. If you wanted to, if you needed to imagine it, arc PR going this direction, oh gosh, is 180 degrees. Half of that would be the 90. Okay. This next one, now it's really kind of pushing us to see what we know. We are looking for arc BC, which is right here. Unfortunately, our inscribed angle, ABC, is intercepting arc AC. I would suggest let's go ahead and find AC first to see if that can help me work my way to arc BC. What would be the measure of arc AC? It would be 94 degrees. Okay. But how's that going to help me find this segment right here? We got to look at the big picture.
You take 94 from 180.
You would. Can you tell me why, what drew you to taking 94 from 180? It was a guess. It was a good guess. I'm going to nudge you in the direction I'd like you to travel. What can you tell me about AB? Segment AB. It's a diameter, which means then that arc ACB is a semicircle, which equals 180 degrees. We know where 94 of it is. So if we take that out of the 180, what's left is our BC. And you said it was 86?
Mhm.
Good. Number 5, this one's a little bit sly because what it's given us are two arcs that have nothing to do with the inscribed angle JKL. So unfortunately, I can't find angle JKL unless I can find this arc right here. Any ideas how I can find arc JML?
Would you add 65 and 53?
Okay, add 65 and 53 and then do what with that?
Double it.
Not quite. So the relationship we have here is just between this angle and this arc. So I know parts of this circle, but I'm missing all the rest. I like where you're going. So we know the whole circle should be 360. So the 65 and the 53 gives me what, 118?
118.
So 65 plus 53 is 118. We know the whole circle is 360 degrees, so we take the 118 out of it. What are we left with? $242. So that is the arc measurement, but we are looking for the inscribed angle that intercepts that arc. We would divide it by 2. So we should get 121.
Mhm.
It's also easy to search. Here's the fact.
The good news is if you can at least fall back on these rules that we're assuming to be true, eventually one of them ties in to kind of give us that breakthrough we're looking for. All right, this next one is asking us to find the measure of angle RST, which is right here, and the measure of angle RUT, which I can stop for just a moment, and I hope we realize that they are both intersecting the same arc, RT. So the good news there is, if they're intercepting the same arc, I already know that whatever those angle measurements are, they are both going to be the same.
Mhm.
They are congruent. The problem, though, is I don't know this intercepted arc yet. But I do have all these other arcs in the circle. I could add them together and then do what with that? Subtract it from 360 again. So 139 plus 75
278.
plus 64, you said it's 278.
Yeah.
So if you then take the 360 of the whole circle, take out the 278,
82.
82 degrees.
Mhm.
Okay, so this arc right here is 82 degrees, which means its inscribed angles that are intercepting it should be half that amount, which is 41. And because they are both intersecting that same
It's the same.
arc, they are exactly the same. Good. So some of them, the last couple there had us doing a few calculations to find them, but for the most part, our values we needed were right there. Now, so we transition to next. We have a few that we are going to probably have to set up some sort of a relationship on to be able to find the missing value. So for these next two, it's asking us to solve for x. So we're going to have to identify where the x is, what we have, what information we have, how they all tie together. So on number 7, we're solving for x. I'm noticing that x is part of an expression that is describing an inscribed angle. And with respect to that inscribed angle, I thankfully have the measure of the arc that it intercepts.
Would it be 8x minus 9 plus 158 equals 360?
Not quite. So the arc is part of the 360, but the angle has its own relationship with that arc apart from 360. So if you recall, up above, we said that the inscribed angle equals half the measure of the intercepted arc. My inscribed angle right now is 8x minus 9, and that's going to equal 1/2 of my intercepted arc, which is 158 degrees. Can I find half of 158? Just divide it by 2, yeah. You get 79. How would you go about solving this the rest of the way then?
Add 9 on both sides.
Add 9 to both sides. Eight x equals, what's that? 88. Divide both sides by 8.
11.
I get x equals 11.
Yeah, I set it up for section at first.
So 360 is going to come into play if we're looking for missing arcs.
Right.
So if we have like all the other arcs and we have part of the circle that's missing, that 360 is going to play a role because we're on the outside of the circle.
Okay.
But if we have an inscribed angle and an arc that is intercepting, that has its own special relationship. That angle is half that arc. Number 8 is kind of similar, except, I mean, technically it's reversed. So here, our x is in an expression that's describing, an arc measurement, Ln. But intersecting that arc is angle LMN, which is an inscribed angle, which means that 67 should be half the arc measure, 4x plus 58. So I'm going to write just that. The inscribed angle, which is 67 degrees, is going to equal half the arc measure, which is 4x plus 58. Now, to solve this one, I'm going to leave that up to you on how you prefer to solve it, because technically, I have two options. I can multiply both of those terms inside that set of parentheses by 1/2. Luckily enough, they're both even. It'll multiply nicely because you're really just finding half of 4 and half of 58. If you don't like that, or if they were odd or anything kind of crazy like that, technically I could multiply both sides by 2, which would get that fraction of 1/2 out of the situation. It's up to you. Would you guys like to multiply both sides by 2?
2.
Or would you like to distribute the 1/2?
2.
Multiply by 2. Okay. So I'm going to multiply the right-hand side by 2, which that 2 and that 1/2 then eliminate. But I also need to make sure I multiply the left-hand side by 2, which is 134, I believe.
So when you do that, because that one basically is like there.
That 1 is attached to the 2. So take quick side note, 1/2 times 2, which is 2/1, equals 2/2, which equals 1, which likes to hide. So that's what's happening there. I just did it relatively quickly. Now, hopefully this doesn't shock us too much, because technically I could have written this as the arc measure equals 2 times the inscribed angle. It's still the same relationship. But now I've got 134 equals 4x plus 58. Subtract 58 from both sides. My mental math is trash, so what'd you get there?
76.
76 equals 4x. Divide both sides by 4. X equals 19. Flip this around. Okay. Going on to the next page. We'll do a couple more here and then I'll give you some answers. I want to eventually get down to some of these later ones. And not to spoil too much of the surprise, I want us to have time to do this giant circle challenge. It's kind of a fun and intimidating exercise to work through. So let's see. Number 9. This one's kind of strange because all it gave me was an expression 13x minus 1. It is for the inscribed angle. What can I set that equal to?
360.
Why 360?
Because the whole circle is 360.
You're right. The whole circle is 360, but this inscribed angle isn't intercepting the whole circle. It's actually intercepting the diameter. So the semicircle is 180. I'm nudging us along that right direction. The angle should be half of that,
90.
90. Or if you wanted to, if you go all the way back when we said an inscribed angle intercepts a diameter, it's automatically a right angle, which means 13x minus 1 equals 90. I would add 1 to both sides. Get 91, so 13x equals 91.
X equals 7.
Divided by 13, we get x equals 7. Gotta be on the lookout for those diameters sneaking in there. Number 10, I wanted to make sure we could do number 10 as well. I'm going to give you 11 and 12 solutions here in just a moment. But number 10 is set up strangely because it's given me a triangle inside this circle. And unfortunately, WY is not a diameter because it does not pass through the center Z. So I'm going to have to go way back to my chapter or my couple of units where I covered triangles. Do I know what this entire triangle set of angles adds up to? So the total should be 180. And here's the good news. I have an angle here of 114. I have the expression holding on to that variable we're looking for in the second angle, but unfortunately, I don't have the measure for angle Y until I take a step back and realize that angle XYW is an inscribed angle and it is intercepting arc XW. Can you then tell me the measure of angle XYW, which is right? How many? So that's my inscribed angle intercepting that 78-degree arc. Every inscribed angle is how much of the inscribed arc? Intercepted arc? 180 is a semicircle. That one's 78 degrees.
would be half.
It would be half. The angle that's intercepting that would be half that measurement there, which I believe
39.
is 39. I would agree. So now I have something for each of those angles. Which means they should all add up to 180. So the 114 plus the 7x plus 6 plus the 39 degrees that we just found are all three angles in a triangle. So the total should equal 180. As I go through here, like terms, 7x is still just chilling out. I need to combine 114, 6, and 39. 159 sounds good to me. Equals 180. Subtract 159 from both sides. So we get 7x equals 21. So x must equal 3. Now, that one technically wasn't the only way we could have solved that one. There was a way where we actually used the arcs to help work our way around. But again, that's the great thing about geometry. There's usually more than one way to approach it based off of what information you have or which information you're comfortable with. Like I said, 11 and 12, I'm going to give you the answers if you wanted to try these later. Number 11, you should get that x equals 9. And number 12, you should get x equals 17. Yeah, similar situations as to the ones we experienced already. All right. We're going to jump through a couple of these because it's more or less the same. We'll probably do 13 and 15. I'll give you the answers to 14 and 16 as we get to those. Number 13, it's giving me a diagram here, this circle. It's telling me the measure of angle FGH, which is right here, is 6x plus 21. And the measure of arc FJH, which conveniently is the intercepted arc, is 17x minus 28. We want to find the measure of arc FJH. Well, in order to do that, we're going to need to find x, because then we can just drop that x into the FJH expression. So what I have here is an inscribed angle intercepting an arc, for which I have expressions for both. So my inscribed angle, 6x plus 21, should equal half the arc it's intercepting, which is 17x minus 28. Well, this is one of those ones where I would probably multiply both sides by 2 again on this one, because distributing a half will give me decimals. So I'm going to multiply both sides by 2. Now make sure you wrap your 6x plus 21 in parentheses, because you're multiplying that whole thing by 2. On the right-hand side, the 2 and the 1/2 are gone. On the left, if I distribute that 2, I'm going to get 12x plus 42. Now on the right, all we have left is 17x minus 28. Well, now I need to get the variable to one side, so I'm going to subtract 12x from both sides. Leaves me with 42 equals 5x minus 28. Add 28 to both sides. $70 equals 5x. Divide both sides by 5. X equals 14. All righty. And then don't mind me while I pretty up my work. Now, oops, I shouldn't have actually boxed it in all permanent like that. X equals 14 was merely the tool we needed to get to our actual answer because we're looking for the measure of arc FJH. So I'm going to
17 times 14.
17 times 14 minus 28. So measure of arc FJH equals 17 times 14 minus 28.
210.
210 degrees. So there we have it. Number 14, very, very similar in the setup. As you work through number 14, if you wanted to try that one on your own, you would get x equals 9, which would lead you to finding the measure of angle STU to equal 29 degrees. Again, if you want to try that one out, see if you're on the right track. Number 15 is awfully sly, just because of how the information is presented to us, how it's set up, and then what it's actually asking us to find. Taking a look at this diagram here, we are given the measure of angle ABD, which is right here, as 6x plus 26. We're also given the measure of angle ACD, which is right here, as 13x minus 9. But then it's actually asking me to find the measure of arc AD, which hopefully draws my eye to the relationship that's going on here. That happens to be the arc that both of these angles are intercepting. Well, there's also an X in the mix, but the fact that these two angles are intercepting the same arc, what does that tell me about the angles themselves? They are congruent because they're both half the measure of AD. We don't know what AD is, but we know that you take half of it, you're going to get the same value every single time. So my relationship here is I'm going to set those two angle measures equal to each other because they should be congruent. So 6x plus 26 equals 13x minus 9. Variables on both sides, so I'm going to move one of those by subtracting 6x from both sides. I get 26 equals 7x minus 9. Add 9 to both sides. Would that be 35 equals 7x.
X equals 5.
Divide both sides by 7, x equals 5.
Does it matter which one you plug it back into?
So that's a good question. Should it matter which one I plug it back into? If they're congruent?
No,
No, they should both give me the same answer, right?
yeah.
Which is why we originally set them equal to each other in the first place. So it's up to you which one you plug it back into. Does anyone have a preference?
6x plus 26.
Okay. So the measure of angle ABD equals 6x plus 26, but the x I can replace with a 5.
86 degrees.
So we get the measure of angle ABD is, you said 56 degrees. Now, be careful. That is the inscribed angle. What am I looking for? Arc AD, which is the arc that angle ABD and ACD for that matter intercepted. Well, if the inscribed angle is always half the arc measure, in this case, what would I do to find the arc measure?
5 by 2.
Not divide by 2. I already have the inscribed angle. I need to multiply by 2. The arc is always bigger than the angle. So the measure of arc AD is 112. And then number 16, if you wanted to try this one out, you would end up getting that x equals 12. And through the use of that, you should eventually end up finding that the measure of arc KL equals 76 degrees. Now, take a moment. We've only spent 2 days processing circles so far, but the two biggest takeaways I would say is central angles, which means the vertex is at the center, equals the intercepted arc that it passes through. Whereas inscribed angles, the vertex is actually on the circle itself, is only half as much as the intercepted arc. Now, the reason why I'm saying try to take a moment to process is because the last page here is known as the the giant circle challenge, for which there are a bunch of angles, some of them central, some of them inscribed, some of them just their own things altogether, vertical and things like that, or vertical and adjacent, things like that. We're going to try to find all the information we can. From that, though, we were given some information. G is the center of the circle. AD is a diameter. That's pretty handy. The measure of arc AB is 78 degrees. So I'm going to put that over here on the side. So AB is 78 degrees. FE is 105 degrees. ED, goodness, is 27 degrees. And CD, running out of cute colors, 42 degrees. So it gave us most of the arcs formed around the edge of the circle, except for BC and AF, which technically I think we could find those. Because if you think about it, if AD is the diameter, that means all these angles here on this side should equal 180, and all the angles on this side should equal 180. Let's go ahead and calculate those real quick, just so we have all the parts of, or all the arcs of the circle. So do you want to do BC or AF first? AF. So subtracting from 180, you want to take away 105 and 27. 48. Okay. And then taking 78 and 42 from 180, we get 60. So now, good news is, we now know every single arc all the way around this circle, which gives me the total 360 degrees. So that's going to be very powerful. It's going to help me start finding some of these angles. All right. So see if I can fit as many of these on here as possible. First off, angle 1 is nestled in right here. So if I follow it out, it's an inscribed angle intercepting which arc? Oop, careful. Follow it out. The endpoints are B and C. So it's intercepting arc BC. So it's intercepting a 60-degree arc. It is an inscribed angle, which means it is half that measure. So angle 1 is 30 degrees. Angle 2, follow its legs out. Where are its endpoints?
A and C.
Ooh, careful.
B.
Angle 2 is right here, so it's angle ABD.
Yeah.
So its endpoints are A and D, which we were told very specifically was a diameter. ABD is an inscribed angle. Anytime you have an inscribed angle that intercepts a diameter, it's on the first page. It's a right angle, which means it is 90 degrees. Okay. Angle 3 kind of squeezed in there. Technically, we could call it angle CBD. It is an inscribed angle intercepting arc CD. It's also inscribed, so it's going to be half that arc measure,
21.
which is 21 degrees. Then we jump over here to angle 4, another inscribed angle, because the vertex C is on the circle. If I follow its legs out, it has endpoints at A and B. Well, arc AB is 78 degrees, so that inscribed angle should be half as much,
39.
which is 39 degrees. Then we slide around here to angle 5. Well, wouldn't you know it? It intercepts the same arc, AB. That means angle 4 and 5 are congruent. They intercept the same arc, AB.
90.
4 and 5. Nope. What was angle 4? We already know angle 4. 39. Guess what angle 5 is?
39.
Also 39, because they're intercepting the same arc. Angle 6. Another inscribed angle. Vertex D is on the circle. Follow its sides out. We have endpoints at A and F. So arc AF is 48 degrees. That inscribed angle should be half as much, which is 24 degrees. Number 7. Do we have enough information for number 7 currently? No, because angle 7, if I follow it out, the endpoint, one of them stops at the center and the other one stops at D. Well, the problem is, since G is not on the circle itself, I can't find 7 yet. So I'll come back to it. Angle 8. Well, shoot. Same problem. Now, while I have it there, though, what can we say about angles 8 and 7 together? If you imagine this whole angle right here, you follow, so AFD has endpoints at A and D, which is a diameter, which means this whole angle right here
90 degrees.
is 90 degrees. Now that 90 is split into angles 7 and 8, and we don't necessarily know that it's split evenly. So that will be useful in just a moment, but I don't yet have enough information to find it. So I'm going to move on to angle 9. Angle 9's right here, kind of to the left-hand side of our circle. If I follow its legs out, it has endpoints at D and F. Okay. Well, this one's a little bit sneaky because its endpoints are including arc FE and ED. What's FE and ED combined to make?
132.
132. So what would half of that be for my inscribed angle? 66. Now, we may not know it yet, but we actually can work our way backwards to find 7 and 8 because we have enough information here. Take a look at this circle. What's special about point G? What's that? It's the center of the circle. So let me ask you this. What would you define AG as if G is the center? Half of the diameter. Yeah, there's a name for this. What do we call a piece that is, what was it? The radius. Well, here's another one for you. What's GF? Also a radius. If you're in a circle, regardless of which direction you go, what can we say about all the radii in a single circle? They're all the same. So that means that AG and GF are the same, which technically means I just formed an isosceles triangle inside this circle, where angle 9 and angle 8 are congruent. Well, do we know angle 9?
Yeah.
How much was it? 66. So guess what angle 8 is?
66.
Also 66. Well, now let's go back a step further. We know that angles 8 and 7 together form a 90-degree angle. We know 8 is 66 of those degrees. It would leave me with 24 out of the 90. So 66 of the 90 comes from angle 8. Take that 66 away, that leaves us with 24 for angle 7. So we keep working our way around here, try to fit them all in nicely. Next up, I've got angle 10, which if I find that, we have another inscribed angle here. Following it out, its endpoints are C and D. Arc CD is 42 degrees, so half of that inscribed angle, for that inscribed angle, would be 21. Now things are going to get a little bit interesting because angles 11, 12, 13, and 14 exist inside the circle itself. So those are neither central angles or inscribed angles. They're just angles, for which now I need to go full triangle mode. Angle 11. If you look at this triangle inside here, angle, or yeah, well, there's not even a point named there. But if you look at the triangle formed by angles 1, 2, and 11, how many degrees should that triangle have?
90,
Oh, careful. A whole triangle has
180.
180. So if the whole thing's 180, do I know angles 1 and 2?
Yeah,
How much was angle 1?
30,
How much was angle 2?
90.
So that adds us up to what, 120?
Mhm.
What does that leave us for angle 11?
60.
60. From there, we jump over to angle 12. Now, if you look at this, angles 11 and 12 are a linear pair, which means 11 and 12 should equal,
60.
oh, careful, 11 and 12 added together, I should say.
120.
Even bigger. It forms a line, be 180. Linear pairs are supplementary. 11 is 60 degrees. If you take that out of 180, angle 12, maybe this is what you're answering, Misty.
120.
Angle 12 will be 120 degrees. How can I find angle 13 relatively quickly?
120 minus 180.
You could subtract it from 180. I could even do it faster. What can you tell me about angles 11 and 13?
The vertical.
They are vertical, which means they are congruent.
Mhm.
So 11 was 60 degrees, 13 is also 60 degrees. What about angle 14?
Vertical from 12.
It's vertical from 12. 12 was 120 degrees, so 120 degrees for 14 as well. Then we keep moving on. Angle 15. Now it's shifting on us a little bit. Angle 15 is actually a central angle because its vertex is G, which is the center. Central angles are not half the arc they intercept. They're equal. So if I follow angle 15 out, it has endpoints at A and F. Arc AF is 48 degrees. So do you know what 15 is? Also 48 degrees. 16 is also a central angle. It would be 105 degrees if you follow its legs out. 17 is also a central angle. It should be 27 degrees. Then we have another situation like we have for 11 through 14. Our 18 through 21. Those exist inside the circle itself. So those are neither inscribed nor central. So 18, if I think about it here, let's see. Do I have angle 17?
Yes.
Do I have angle 6?
Yes.
So I have 2 of the 3 angles in this little skinny tiny triangle in here. 17 was 27 degrees. 6 was 24 degrees, which is what, 451 degrees total?
Yes.
If you take that 51 from the 180 that belongs to that triangle,
129.
you get 129 degrees.
And 20 is vertical from 20.
Good. 20 and
So it's the same.
20 and 18 are vertical, so it's also 129 degrees. So now I just need to find either 19 or 21 because they are vertical as well. So I'm actually going to go back to 18. 18 and 19 are a linear pair, therefore supplementary, therefore should equal 180. Take 129 from that 180, we get 51.
21 is the same.
21 should be the same as well because they are vertical angles. And just like that,
You're not gonna have one of these on the test, are you?
no,
Okay, thank you.
no, I won't put one of these on the test. So with a little bit of work, you can pick apart pieces and find your way through. Now notice, not only did we use some key terms that we introduced with circles, which were central angles and inscribed angles, we still had to fall back on some of our old things like triangles. You know, all 3 of their angles equal 180 degrees. Vertical angles are always congruent. Linear pairs are supplementary, therefore they equal 180 degrees. So we still have to fall back on some of those key definitions. So they're not completely gone because, especially when you're dealing with shapes, odds are you can take one big shape and have a lot of little different shapes inside.
So the triangles go back.
The triangles always come back. The triangles never went away, if we're being honest.
Yeah,
The
you're right.
triangles are always going to be there.